Welcome to topic 8.5. We are going to work on predicting the products of single replacement reactions. So similar to 8.4 in that we're predicting products. Now we're switching gears to next reaction type. There are some different things going on with this particular lesson, so you do need some different supplies. Please have your periodic table with charges, track down your polyatomic list. That's going to be useful. And then if you have the ability to print, this is the new resource table for this lesson or this unit so far, which is called an activity series table, or in this case, they call it a chart. Okay, so single replacement reactions we introduced with reaction types. And so there's a few things that go on with single replacement. So in single replacement, there's obviously replacing taking place because of the name, and the single part is telling you that an element comes in contact with a compound. So that's the single part. This is the single. And so what takes place in this reaction, if it's able to occur, is that we have an element that gets released from the compound and a new compound forms. There are two different ways that replacement can occur. One way is that a cation can replace another cation within the reaction, or an anion for an anion. So the idea here is when we go to look for what is the outcome of a single replacement reaction, only like charges can recombine. You cannot have a compound that ends up with two cations together or two anions. A cation will always exchange places with another cation, and the same goes for an anion. So in this instance, we have a compound, AB. It's reacting with element C, and what is the outcome going to be? So in this instance, I'm trying to show you that C is an anion, and so that means that in this reaction, it will switch with the anion, and I can safely assume that B is the anion because of the fact that it is wrote second in the formula. Therefore, the outcome B is now on its own, and AC forms the new compound. So like I mentioned up above in number 2, is a cation can also exchange for itself. So A, being the cation, can exchange with B. B ends up on its own, and we end up with AC in this case. So again, what's taking place here and how these two are different from one another is that we had anions here that exchanged, and I can include that in the descriptions, anion exchange, and the other one is showing a cation exchange. Okay, and so the thing that I mentioned is that reactions don't always occur. So we're going to just go with the safe assumption that everything I provide you in synthesis decomposition will occur. Now, is that 100% true? No, a reaction doesn't always necessarily occur. And so with single replacement, we have a resource to help determine if a reaction is going to take place or not, to then see if it's even worth our time to figure out what products they make. And that's where this activity series comes into play. So the activity series, this one is, I like this one compared to others that are out there. So there's two different series within here. We have one that's comparing the metals and one that's looking at non-metals, specifically the halogens. So anytime you have to look for a metal, you're going to be looking on this side. And gold is at the bottom of the list, meaning it's the least active out of these provided metals. As you make your way towards the top, lithium is the most active metal. Now, on the nonmetal side, it follows the same pattern where we're looking at just the halogens, family 17. And so iodine of that family is the least reactive, and the most active is fluorine, and that goes into electronegativity differences between these different elements. And so this rule here tells us that elements cannot replace anything above them. The reaction does not occur in this situation. So we're going to start looking at that here in a moment. So the thing we're going to do first is just quite simply look at our activity series and determine which one's more reactive. So in this first one, we're comparing calcium to tin. So I know that they are both metals, therefore I know I'm going to look on the left-hand side here. So here I found tin and I found calcium, and we know that as you move up the list, the more reactive or active they become. Obviously, calcium is much further up the list, therefore calcium is more reactive. In letter B, we have aluminum or potassium. Well, here's potassium, and we have aluminum here. The only way aluminum would be more active than potassium is if it was the one element above it, which it is not. Therefore, potassium is the most active. Now we're comparing iodine or chlorine. So that's when we're going to go to the right-hand side here. So when we take a look at their comparison, we have iodine and Cl. Cl is further up the list, therefore Cl is more active. And then the last one, bromine or fluorine. Fluorine is at the top of the list, therefore it is the most active over chlorine, bromine, and iodine in the halogen family. So that's going to become important here in just a moment as we start looking at products. So I broke these down into two kind of sets of examples. So this first one in section D is looking just at cations. So what do we do in a single replacement reaction when we're working with a cation? And how you know that is the first thing I would do is we have lithium. Lithium, I can see, is on the left-hand side here. So lithium is only going to try to replace another cation because it is a metal. So if you go back and remember that in our naming formula system, we have the metal always listed first or the cation first. So we have to compare the reactivity of lithium to fluorine, or not fluorine, but iron. So we have to look at, is lithium more active or less active? Well, we can see here that it's at the top. And so that's going to help us with the explanation. So yes, the reaction will occur. And the reason why is lithium is above iron, making it more active. Okay, so like synthesis and decomposition, there's some steps that go into play of what we need to do to correctly identify the products and outcome of this reaction. And so when we take a look at working through this, we have lithium and iron, and then we have nitrate. So in order to predict the products and knowing the reaction is going to happen, we need to know what the final formulas are going to look like. So the first thing is, and I like to have things follow a pattern. I always like to write my first new single element on its own. Well, lithium is what's exchanging with the iron. So iron is going to be my first product that I'm going to write. And the reason with that is the next thing is the symbol is just going to be Fe, and then you have to remember your Hoffman-Kleibers for your diatomics, and iron is definitely not one of those, so it's just Fe. So when it comes to the part of figuring out our new compound, we need our charges. So when you go to your periodic table, lithium is a +1 cation, and then nitrate, if you take a look through our list, it's a -1 polyatomic. So to get our compound formula, we have lithium +1, nitrate -1, so no new subscripts and no parentheses are needed, and we get LiNO3. So then the last thing is, because of charges and where subscripts were on the previous side, we need to conserve mass by adding coefficients. Our lithiums are balanced, our nitrates are not. We have 3 on the reactant side, therefore we need 3 on the product side. We need to update our lithium to 3 here. I can put in 1s here or leave it blank, and our first example is done. So here in example B, we have Au and HCl. So the first thing is we have to figure out what side of the activity series we're using and if the reaction can happen or not. So when we go to look, we have Au, which is gold, and we have hydrogen as our cation. So we're comparing our two metals. Again, hydrogen is listed first, therefore that is our metal in the acid here. You can see that of all the metals, gold is listed at the bottom here being the least active. So that means gold is not able to replace any metal above it because of its activity series being so much lower than everything else. So that's why it's really important that you look at this first, because you're going to love the answer that we need to put. We put no reaction, and we're even so lazy that we abbreviate reaction as RXN, and we're done. Again, the reason why we're done is no reaction will occur. And the reason why is gold, or Au, is below H, or hydrogen. Au is less active. Okay, so again, you didn't have to go through all these steps to then go back and say, well, it's not even going to take place. So that's why you need to use your activity series first. So now the next section is the same premise, but we're going to use anions. And so again, the reason why I know that they're anions is chlorine is a nonmetal. So what I need to look for is what nonmetal is it going to try to replace? Well, potassium is listed first, therefore that's my cation. So bromine is my anion. So we're looking at can Cl and Br exchange places. So we use our activity series like below or up above, but we need to use the right-hand side comparing nonmetals, and we're comparing chlorine to bromine. Chlorine is further up the list, meaning it is more active. So yes, a reaction will occur. Chlorine is above Br, so chlorine is more active. So when we start taking a look at products, again, I like to put whatever is going to be on its own first. So bromine is now going to be on its own, and it is Hoffenkleiber. So its formula is going to be Br2. And then we need to work on coming up with our formula for our compound. Again, keeping rules straight, your metal goes first. So what's left? Our metal is potassium. If you utilize your periodic table, potassium is a +1 cation. It's combining with chlorine. Again, chlorine is only Cl2 when it's on its own Hoffenkleiber. It's only diatomic in that situation. When you get to the point of writing out its formula within a compound, you leave the subscripts behind, you write Cl, you write its charge, you cross accordingly, and you get a formula of KCl. Again, your subscripts are not always going to match on the reactant side to product side. That's why we then go back in with coefficients to balance. So then from here, I can see my chlorine are not balanced. A2 will take care of that. That throws off my potassium. 2 will take care of that. And in doing so, that fixes the bromine, which then fixes those. And I now am complete. Our next example continues on the backside here, and we have iodine reacting with table salt. So again, we have iodine. What is it going to try to replace? Well, iodine is a nonmetal. Therefore, it will try to replace our nonmetal, an anion for an anion. So iodine is here. It is the least active of the halogens. Therefore, it is not able to replace any elements above it. So when iodine is on its own, no reaction is going to take place. So no reaction. And these are the ones we love. And so when it comes to our reasoning, iodine is below chlorine. That means that iodine is less reactive than Cl. And so then we are done. All right, so the last bit is 3 practice problems. I would highly recommend at this point you pause the video and then come back to it and see how you compare to what I got. So looking at Mg reacting with AgNO3, first thing you have to do is compare reactivity. Magnesium is a metal, therefore magnesium is going to attempt to replace my Ag. Magnesium is here. Ag is the third one from the bottom. Therefore, yes, the reaction will take place. So you need to get to the point of predicting products. Again, I like to write what's single first. My new single element is going to be Ag, which is not Hoffenkleiber. So that's my first product. My second product, again, you have to write your metal first, your positive, combined with your nonmetal. Magnesium is +2. NO3 on your polyatomic list is a -1. So the correct formula for your compound on the product side is MgNO3 2. The last step is we need to conserve mass by balancing A2, and A2 will take care of that. And that is the correct answer for example A. In letter B, we have sodium fluoride reacting with bromine. So I have to look at what is bromine going to try to replace. Bromine is a nonmetal, therefore it's going to try to replace the fluorine. We can see that bromine is below fluorine, therefore my single element is less reactive than my element that's in the compound, therefore no reaction is going to take place. And this one is done. Very last example then, we had aluminum with copper 2 nitrate. Comparing the two metals, because aluminum is a metal, it's going to attempt to replace copper. And yes, my single element is more reactive than the one in the compound. Therefore, yes, the reaction will take place. In this instance, copper is going to be my single element now. It is not Hofenkleiber, so it's just Cu. My new compound is aluminum combining with nitrate. So we have aluminum with a +3, nitrate with a -1. The new formula then is Al, NO3 in parentheses, a 3 outside. I then go through the process of balancing. I'm going to have to get the nitrates to 6, so a 3 and a 2 will fix that. A 2 in front of the aluminum, a 3 in front of the copper. We are then balanced. Last thing is, just for example, for products, the order does not matter in terms of what is first in terms of the single element or the compound. So you could have had an answer like this, and these are both completely acceptable. But you need to always make sure that your compound is following the rule of that order does matter, cation first, anion second. And so that's how you use the activity series to predict products of a single replacement reaction. If you have questions, please let me know.